In this video, we're going to be looking at some optimization problems, and this is our first problem here. So I'll explain the content of the question, and we'll work out the answer to the question. So we have a string, and that string is 200 centimeters long. With that string, we turn it into a rectangle like such, and we work out that the area of this rectangle can be written as some equation length times width. And they've told us that this length here is simply x. Our goal is to work out the maximum area of this entire box here. So the first thing we're going to do is we're going to generate an equation to work out what the area is, in terms of this value x. So if we have an area function in terms of x, we can then use calculus to find the maximum area. So first thing we can recognize is the area is simply x times by y, and I'm going to label this side length here as y. But it would be nice if we were able to replace this side length with something in terms of x. So what we can do is we know that this other side length here is x as well. And if we want to solve for y, we can say that x plus x, so 2x plus 2y, okay, the sum of the lengths of the sides of this box is going to equal to the length of the entire original string, which was 200. So now we can rearrange this for y and say 2y equals to 200 take 2x. That means y equals to 100 minus x. So in other words, the area of this box here is really just the same as x times 100 minus x. Nice. So now that we have this here, we can now use calculus to determine the maximum area. So first thing I'm going to do is I'm going to expand this out. So we get 100x minus x squared. If I calculate the derivative of this function, dA on dx, okay, the derivative is simply 100 minus 2x. To work out the maximum of any function using calculus, we would always have to make the derivative equal to 0. This is the point at which there exists a stationary point. So if there's a stationary point, okay, over here, the derivative is equal to 0. It'll be a maximum because the derivative is 0. That would mean that x is simply equal to, in this case, 50. Okay, x is 50 centimeters. So we have that x is 50 centimeters. So we know this side length is 50, this side length is 50. So to work out y, the side length of the other side, it's just 100 minus 50. So y is also equal to 50. That means the maximum area of a box here will be in the form of a square. So the maximum area will be in the form of a square like such, where all four sides are 50 centimeters long. So to work out the maximum area, we worked out that the maximum area happens when x equals 50. But in relation to this box, we know the area is just 50 times 50. And that'll give us 2,500 centimeters squared. So this is the maximum possible area of our box. And the x value which gives us this maximum is 50. Okay, this is our next question here. We are given a blueprint for a piece of metal which we can fold into a box. So we can fold this entire shape into a box like this with an open box. And the way we do this is the question has told us that we start with a square piece of metal and we have cut out notches in that metal. We have cut out these notches in the metal. And then what we can do is we can fold up these rectangular pieces upwards. So we can fold them up like such and we can get a box. So our goal is to first work out an equation for the volume of this box, and then hence work out what is the maximum volume that this box can occupy. And the way I'm going to do this is I'm just going to label each of these notches, or the length of these notches, I'm going to label them as x centimeters. Okay, so we know that the length of the entire width, or the width of the entire square here, if we have an original square, is 6 by 6 centimeters. So this is 6, this is 6, this is 6, this is 6. And we cut out little notches of x centimeters. So to work out the length of one side of our square in this case, we can take the original 6 centimeter side length and minus away x from this section here, and minus away x from this section here. So what we get is the side length that is represented by this over here is simply going to equal to 6 minus 2x. Okay, so this will be the length of our box. And the width of our box will simply be this over here, because remember, this section is going to be folded up. So it'll look like a box like such. Okay, so it'll be an open casket box like this. Okay, so this is the sides. These are the sides. And then the open top is just this top section here. So this is the length of our box first. So we worked out that that is the length. The width is also going to equal to 6 minus 2x, since it is a square that we're cutting this piece of metal from. And the height of the box is simply the height of our notches. These heights of the notches will give us the height. So the height here is simply going to be x. So to generate an equation for volume, we know that volume is simply length times width times height for a rectangular prism. And if we sub in the values for x, or in this case the lengths, widths, and heights, we can say that the volume is going to be, in this case, x times 6 take 2x times 6 take 2x. Length times width times the height. So let's now work out the maximum value for this function using calculus. So first thing I'm going to do is I'm going to expand all of this out. So I can have the x on the outside and simply expand this bracket here. So that would give me 36 minus 24x plus 4x squared. And then I can expand out the x. So if I expand out the x, I get 36x minus 24x squared plus 4x cubed. Now we can differentiate and solve to work out any stationary points. dA on dx. That's going to simply equal to 36 minus 48x plus 12x squared. And the reason we want to differentiate and let this equal to 0 again is because if we have a graph for a quadratic, or in this case a cubic, the volume function was a cubic, we want to work out, okay, what x value gives a maximum. We want to work out what is this x value that gives a maximum, and hence what is the maximum volume. And if I draw a tangent line at this maximum, you can clearly see the derivative or the gradient is 0. So that's why we're differentiating and working it out to be 0 at this point. Okay, so let this equal to 0. So we get 0 equals to 12x squared minus 48x plus 36. And what we can do is divide everything by 12. So we get x squared minus 4x plus 3. And we can solve this quadratic by simply saying x take 3, x take 1. So that means the two values of x which allow the derivative to be stationary is x equals to 1 and x equals 3. So which value one between these two makes the volume a maximum? Well, you would expect it to be the value of x that is bigger, right? You would expect x equals 3 to give you the maximum and this to give you the minimum. Well, not so fast. Okay, we have to verify this using the sign test. So I'm just going to test it on x equals to 1. So if I have x equals 1 and I draw out my little sign test like we did in another video, if you're not sure how to do this, I do have another video, so go watch that before you watch this. So we have x, dy on dx, and the sign. And we also have 3 columns for 3 x values. The one in the middle is the one that we're testing. In this case, we're testing for when x equals to 1, because that's one of our stationary points. We know when x equals to 1, the derivative is 0. That means the tangent line will be flat like this. I'm going to test an x value slightly less than 1, so in this case 0, and an x value slightly more than 1, so 2. So the derivative when x equals to 0, I can simply work that out by plugging it into my derivative equation. Okay, so I'm going to highlight this equation just to make life a little simpler. So to work out the derivative when x equals 0, sub in x equals 0. And we get that the derivative is simply 36. Then when x equals 2, just sub in x equals 2, and we can work it out. This equation here is really just a simplified equation of this. So we will still retain the sign, either a positive or negative. So I'm just going to sub in 2 into this equation instead, just because it's nicer. So in this case, we get 2 squared is 4 minus 8 plus 3. And in this case, I don't really care what the number really is, but just by looking at it, I can tell that it's just going to be a negative number. Okay, so it's a negative number here. So what that means for these two x values here is when x equals 0, the gradient of my tangent line is 36. So it'll be a gradient looking rising like this. The gradient will rise. Then when x equals 2, you know the gradient is negative for the tangent line at x equals 2. So the tangent line will look like this. So if I connect these points up together, I can see that it's forming some sort of shape like this. Okay, it's rising from when x is less than 1. When x equals 1, it's flat. Then when x equals more than 1, it's going back down like this. So that simply means this is the maximum. So the value that gives you the maximum is actually x equals to 1, not x equals to 3. Okay, so in this case, I'm just going to say we can reject x equals to 3 because it actually doesn't give you the maximum. I'm pretty sure it actually gives you the minimum, but you can verify this yourself. So that means x is equal to 1. So now we need to work out the volume that is given when x equals to 1, because this volume is the maximum. So if I sub it back into our volume equation was simply this. So if I sub in 1 into our volume equation, we get 36 minus 24 plus 4. And that's just the same as 36 minus 20, which is the same as 16 meters cubed, or in this case, centimeters cubed. So this is the maximum possible volume for a box in these conditions. And this is how you do optimization for a question like this. Okay, this is our next question. A cuboid has a total surface area of 150 centimeters squared and a square base of x centimeters in the length. So what is the maximum volume of this cuboid? So let's just draw a diagram, get some equations. Let's do something first. So a cuboid is a shape which is not really a cube. It could be a rectangular prism or it could be a cube. Something which just has 6 sides and looks like a cube pretty much. So for example, we have a square like this. We could have another square like this. We have 2 squares, and then we could connect them up with the following arrangement like this. So this here is a rectangular prism, but we would still call it a type of cuboid. Okay, and we can say that this length is the same as this length is the same as this length, like this, because it says we have a square base, so this base is square. So what we're going to say is it has a length of x centimeters, and we know that the height, actually we don't know what the height is, so we're just going to say the height is h. This is what we're going to rearrange for. We want to have just one nice variable in our equations, so we're going to say x is our variable. So let us first determine what the value of h is, and they've nicely told us that this total surface area is 150 centimeters squared. So let me first generate an equation for my surface area. So if I have this shape here, I know the surface area is going to be the surface area of this side times by 2. So it'll be x squared times 2, 2x squared, plus 2 times the surface area of this side, because we have 2 of these sides. And the area of this rectangle here is really just x times h, so 2xh, plus the area of this side length here times 2, because you have 2 of them. And again, this side length here is x times by h. So it's also 2xh. So the surface area simplifies down to 2x squared plus 4xh. And we know the surface area is equal to 150 because they've told us in the question. So now that we have this, let us rearrange and eliminate the variable h. So if we rearrange and eliminate the variable h, we get 4xh equals to 150 minus 2x squared. That means h is equal to 150 minus 2x squared all over 4x. So this is our variable for the value of h. Okay, so this is what we get for h over here. I'll do it in a nicer box. Like this. So now that we have the value of h, I'm going to erase all this working out just for space. Okay, we're still not done with the question. We need to work out the maximum volume of the cuboid. So why did I bother rearranging this for a whole time? Why did I bother working out h in terms of x? I'll show you why. If I want to work out the volume of this entire shape, okay, the volume is simply the length times the width times the height. The length is x, the width is x, and the height is h. So that would mean that volume is equal to x squared h. So if I try doing calculus on this, I have an extra variable that I have no idea about. But luckily, we just rearranged for h in terms of x. So now what I can do is I can rearrange the h, and I can say it's 150 minus 2x squared all over 4x. Okay, and we were able to do that because they told us the original surface area was 150 centimeters squared. So let us now get cracking into the calculus section of this. So if I want to differentiate, I first need to expand these brackets out to work it out. So if I have it, it's 150x squared minus 2x to the 4 divided by 4x. Okay, this then simplifies if you want to rewrite it as a polynomial. 150x squared divided by 4x. Okay, that's the same as 150 on 4 x minus 2 on 4 x to the 3. We know 150 on 4 is the same as 75 on 2, so I'm just going to write as 75 on 2. And then 2 on 4 is the same as a half. So our volume equation is simply this. So now we have one nice equation in terms of the variable x. So let us now differentiate. dv on dx, so the derivative of our volume with respect to the variable x, is equal to 75 over 2. And then minus 3 on 2, x squared. So now if we solve this for 0, again, we want to find out when the stationary points are occurring for this equation. So we get this. So what I can do is I can first times both sides by 2 and then rearrange to get 3x squared equals to 75. That means x squared equals to plus or minus 25. So therefore, x is equals to 25. So that means x is equal to plus or minus 5 centimeters. But let's be sensible here. We know that in the context of this question, x is the side length of a shape. When has the side length of a shape ever been a negative value? Okay, so we never talk about side lengths in reference to negatives. So we can almost say in this question to reject the negative solution because side lengths are never negative. Okay, so that means the only solution we can worry about here is x equals to 5 centimeters. So x equals to 5 centimeters is the value that gives you the maximum volume in this question. But they asked us what is the maximum volume. So to work out the maximum volume, let's work out the volume when x equals 5. Okay, that's simply going to be equal to 75 over 2 times 5 minus 1 on 2 times 5 cubed. Okay, and this does look a bit hard to do by hand, but let us do it anyway. So on the top, we get 75 times 5 minus 5 cubed times 1, or just 5 cubed, all over 2. Okay, to do it by hand nicely, I can rewrite it as, I can rewrite this section here as 25 times 3 times 5 minus 5 cubed all over 2. And 25 times 3 is 75, but 25 is the same as 5 squared. And if I do 5 squared times 5, that's just 5 cubed. So this is really the same as 3 times 5 cubed minus 5 cubed all over 2. So 3 times 5 cubed minus 5 times 5 to the power of cubed, is the same as 2 times 5 cubed. And 5 cubed is just 125. So the final answer would be 250 divided by 2, which is just 125 centimeters cubed. So this is the final volume of the shape of the cuboid that gives us the maximum volume. So the maximum volume is 125 centimeters cubed. Okay, this is our next question. We've been told that the volume of a cylinder equals to pi r squared h, and we need to find the maximum value of volume if we are told the condition that r plus h equals 12. That makes our life very easy. We can rewrite this entire equation in terms of just one variable. In this case, I'm feeling volume in terms of radius, but you can also do volume in terms of height if you'd like. So first, I need to work out what the volume is by replacing the variable h with an r. And they've told us in the question that r plus h equals 12. So that simply means h is equal to 12 minus r. Very nice. So now we can replace the volume of a cylinder equation for pi times r squared times by 12 take r. And if you want to work out the maximum, we must make this into a polynomial first. So v of r equals to pi, well in this case 12 pi r squared minus pi r cubed. So let us maximize this equation and work out the maximum. So dv on dr, the derivative of volume with respect to the radius, is equal to 24 pi r minus 3 pi r squared. And if we have this, we need to find the stationary points to this. So that would mean that 3 pi r squared equals to 24 pi r. We can cancel one set of pi's. We can cancel the 3's to leave an 8 here. And we can cancel out the r's to get an r here. So that just means r is equal to 8. Okay, but you cannot just do that. Okay, because it's a quadratic, okay, this was kind of a test, we have to work out the other solution on both sides. So here, what we have to do is we have to rewrite it as 3 pi r squared minus 24 pi r equals 0. That means we can factorize out a 3, a pi, and a r, and then we'll be left with an r take 8 equals 0. So that means the radius can either equal to 0 or it can equal to 8. Okay, but obviously the radius can't equal to 0. That would definitely not maximize the volume of anything. Okay, but we still have to show this. We still have to show this step. So we can then reject 0 because it's just nonsense. It's tomfoolery. So the radius is simply equal to 8. Okay, so 8 centimeters is the radius. So what is the maximum volume then? Well, the volume when x is equal to 8, or in this case the radius equals to 8, is this equation here. So 12 pi r squared take pi r cubed. Like this. And we can factorize, in this case, an 8 squared. So we can say 8 squared, and then we're left with a 12 pi minus an 8. Okay, so that means it's equal to 64 times 12 pi take 8. Okay, so I'm just going to leave it like this, but that's how you work out the maximum volume here. Okay, and this is our last question. So we are told that a piece of string that's 10 centimeters long has been cut up into 2. It's been cut somewhere along the string. They have not told us. And they've told us that they've made 2 squares. They've made 2 squares out of this one piece of string. And we need to find the maximum total area of both of these squares. So first, let us work out what is the area of both of these squares in terms of x. Well, the area of this square here is just x squared. Okay, that shouldn't be too difficult. But we don't even have a side length for this square, so how do we even work out the area of this one? Well, we know that the sum of the perimeters of both these squares should equal to 10, because the width and length of these squares, right, they originally came from this piece of string here that was 10 centimeters long. So what we can say is 4x, which is the length of 1, 2, 3, 4 sides of this square, plus 4y, and I'm saying 4y because we're just going to label this side length as y. Okay, so this side length times 4, okay, should be equal to 10 centimeters. And we don't know what y is, so let us just work out what y is currently. So to work out y, we can say 4y equals to 10 take 4x, and that means y is simply equal to 5 minus 2x all over 2. So this is the value for y. I can also simplify this as 5 on 2 minus x. Okay, so let us now work out, okay, what is the area? How do we work out the maximum total area of both of these? Just for space, I'll get rid of all this. Okay, so now that we have this here, we know that the area of both of these squares is going to equal to x squared plus 5 on 2 take x whole squared. Okay, because that's the length of this side length here. So instead of y, I'm going to replace it with 5 on 2 take x. That's the length of this side. Okay, and if you times it by itself again, because it's a square, you get this as the area. So let us just expand this out just to make it look nicer. X squared minus, in this case plus 25 on 4, take 5x plus x squared. So we get the area is equal to 2x squared, take 5x plus 25 on 4. Okay, so now we can maximize this equation here. So dA on dx, so the derivative of area with respect to x, is going to equal to 4x minus 5. So that means if you want to work out what the value of x is, okay, we need to first let the derivative equal to 0. So that means x, the value at which x maximizes the area, in this case, is going to be 5 on 4. So that's the value of x that maximizes the area of both squares. So find the maximum total area of both squares. So to find the maximum possible area, we need to sub it back into this equation here, because this is the area formula. So area, when x is equal to 5 on 4, that's going to be 5 on 4 squared plus 5 on 2, take 5 on 4 squared. So this is going to be the same as 25 on 16, and plus inside here, this is the same as 5 on 4 squared, okay, which is also equal to 25 on 16. So that would equal to 50 on 16, okay, which is also going to be equal to 25 on 8. So this is the maximum possible volume area that you can get. And it makes sense that to find the maximum possible area, that both the squares would have to be the same dimensions, because it makes intuitive sense. But this is how you do optimizations for questions like this.